Hi, welcome to Lesson 18b, Anti-Differentiation. The goal of today's lesson is to calculate the area between functions and the x-axis. So the idea of this anti-differentiation thing is basically we're doing the opposite of differentiating. So we've looked at functions in the past like this, say x cubed, and then so f of x equals x cubed. Then f prime of x would be 3x squared. If we say y equals, for example, 5x to the power 4 minus x cubed plus 3x squared, etc., etc., then the differentiation, or the derivative, is 20x cubed minus 3x squared plus 6x. Actually, I'm going to go a little bit further here and say, let's say this is 2x minus 5. Okay, and then we go plus 2, and that minus 5 just becomes 0, so it drops out. Okay, so the antiderivative is the opposite of differentiation. So basically what we want to do is, if we go for differentiation, if we start with y, or f of x, then differentiation is taking us to dy by dx, or f prime of x. Actually, I'll put a little or in there as well. And so that's differentiation. And then anti-differentiation, which is the opposite of differentiation, is going from here to here. So we're going from the derivative back to the original function. Okay, so that's what we would be doing, the reverse process basically. So we can say that some function, now I'm using capital F, so uppercase F is an antiderivative of some function f on any interval if capital F, so uppercase F prime of x equals f of x. Okay, so this is the antiderivative of this. If, when we take the derivative of this, we get that. Okay, so we take the derivative of this uppercase f of x, we get lowercase f of x, then that means that uppercase f is the antiderivative of lowercase f. Okay, so we're just going to go backwards. So suppose we start with a function, and we'll start off nice and simple, x cubed. Well, if we want to find the antiderivative of this, let's first consider g of x equals x to the power 4. Then g prime of x is going to be 4x cubed. Okay, so we've got the power part that we started with, but here we've got a 4 that we don't have here. Okay, so if we're going to go backwards now, f prime of x, or sorry, f of x is x cubed, then uppercase f of x, well, we know it's going to be x to the power 4, because when we take the derivative of this, sorry, I keep losing track of that, we know that uppercase f of x is going to be some power 4, because when you take the derivative of it, you get 1 degree less. So when we took this derivative, we got 4x cubed. Well, we want the x cubed part, but we also want a coefficient of 1. So if, when we take the derivative of this, the 4 comes down in front, then we want to negate that 4. So what can we do? What can we add in front of this to negate that 4 when it comes down in front, so that we end up getting a coefficient of 1? That would be correct. We're going to multiply by 1/4. So when we take the derivative of this, the 4 will come down in front. 4 times 1/4 is just 1. And then we subtract 1 from the exponent here to get this cubed. Okay, so that's how we'll go about finding the antiderivatives. Okay, so it's a little bit of a guessing game at the beginning, but we're using a bit of logic with that too. Okay, so let's now try, let's find the antiderivative of 6x cubed minus 8x. But we're going to find the antiderivative of this by first differentiating x to the power 4 minus x squared. Okay, so notice that we're going to differentiate this by increasing this cube up to x to the power 4 and this unit power to squared. So to take the derivative of this, we're going to get 4x cubed minus 2x. Okay, so we have the power we want for the first term and the power we want for the second term, but we need to do something in the front here so that we get 6, and we need to do something here to get this 8. Okay, so capital F of x, or uppercase F of x, we know it's going to be x to the power 4 and x squared, so that when we take the derivative of it, we'll get an x cubed and just an x. Now, what do we do? We'll do this one first. What do we do? What are we going to multiply this power by as it comes down to give us an 8? Well, we're going to start off with a 4 there. Okay, so when you take the derivative of this, the 2 that comes down in front, 2 times 4 is 8, gives us this. So that takes care of that. And then now here, we know that when you differentiate this term, the 4 comes down in front. Well, we don't want a 4 in front there, we want a 6. So what can we do to this, or here, so that we get a 6 when we multiply by 4? Well, 4 times 1 is just 4. 6, if you take a look at the value of 6, 6 is 1.5 times that of 4. So we can multiply this by 3/2. So 3/2 is 1.5. 4 times 1.5 will give us 6. Or another way of looking at it, 4 times 3 is 12, divided by 2 gives us 6. Okay, so this is then the antiderivative of this original function here. Okay, so now we're going to proceed on to 18C, the fundamental theorem of calculus. So we've been looking at antiderivatives. We looked at area under the curve in 18A. Now we're going to take a little look at an investigation in your textbook from page 450, and we're going to take a look at areas under the curve again. Now this time the curve will be a function of some sort that were known. So suppose the given function is x equals, or y equals 5, so f of x equals 5. This is this horizontal line here. And we're going to look at it between some value x equals a and some other value x equals t, some unknown that we're not sure of, and that can change anywhere. So x equals a is this firm constant that we do know that x equals, and this other value is some other random variable that we're going to call t. So notice that this is a rectangle. Now it could be a square, but we know for sure it's a rectangle. And so if we're to find the area of this, we can use the area notation, which has been given to us. So the area notation tells us that it's the antiderivative of 5, or so this function, f of x equals 5, or y equals 5, evaluated between t and a dx, which that's just part of the notation about finding the antiderivative. So this area that we're going to look at is the shaded area under the graph here. And if we look at this, we notice that the height all the way along here is 5. And the length, or the width of this, is t t minus a. So this whole distance here, of course, is t, and this distance here is a. Therefore, the difference between them, so the length of this rectangle, is t minus a. So we get t minus a times 5, which is just length times width, or base times height, whatever. And then if we expand this 5 in, we get 5t minus 5a. Okay? And so then we can simplify this, and we can say that a of t is actually capital, or uppercase, f of t minus f of a. F of t, so if we took the antiderivative of f of x equals 5, like we just saw, capital F of x would be 5x. Okay, so this is f of t equals 5t, which can be simplified to 5x. Okay, so if we took the derivative of uppercase f of x equals 5x, how does that relate to the actual function f of x? Well, when you take the derivative of this, we actually get the original function once again. So that uppercase f of x is, as we now know, the antiderivative of the original function f of x. Okay, so let's move on to another example here. So here, I guess, sorry, just to summarize this, we can now see that by taking the area here, we're actually finding the antiderivative of this original function. So just like in the past when we were taking the derivatives from first principles, we noticed that the derivative of a function was the slope or the gradient of the tangent to the function at any point. Now we're noticing, and we'll notice in the next little while too, the next few examples, that the antiderivative of any function comes from the area under that curve. So we're going to take a look at this other example here. So this is part of the investigation as well. Number 2, here we have the basic of all functions, f of x equals x, or y equals x. And again, we're going to take a look at the area under that curve from x equals a to x equals t. So if you really look at that, now we could, if we really wanted to, make this into, or look at this as a composite figure of a triangle plus a rectangle, but it's much easier to look at it as a trapezoid, or a trapezium, where the two parallel sides are a and t, because if y equals x and x is a, then that means at this point y equals a, and at this point y equals t, and the height between those two parallel sides is t minus a.